we will split the time to talk about different things, and hopefully you'll get a better perspective of what we do there in the University of Lisbon. The things that we'll be talking have to do with the earlier projects in which we have been involved, and in these projects, so we have just saw a very nice presentation about real stuff for airplanes. We are not going to talk about these kind of things because we work on a little more, let's say, high level on the software side, on middleware or operating system stuff. And we tried to address things that have to do with time and space partitioning and architectures and system architectures to deal with problems of timeliness and ensuring the requirements of the applications with respect to timeliness and safety. So this is what we will be talking. Before everything, so I was saying to you that we come from this LASIG research unit. In the LASIG research unit, there are few research groups. We are from the navigators group, and these are the 6 professors that are in this group, and we have around 14 PhD students at this moment and a few more master students. So basically in our group, not in LASIG, so the key word for LASIG is really something that we try to do very ambitious research in many fields, but in our particular group we try to look at things that have to do with embedded systems and security in particular, and the target areas are, as you can see here, I don't know if this is working, yes, so real-time safety for automotive, aerospace and environment. So basically we have 2 research lines. One research line more focused on the security aspects, another one more on embedded systems. In overall we have a very good knowledge on our, let's say, DNA comes from the dependability and fault tolerance areas, so we try to develop solutions in terms of middleware architectures for more dependable systems. And essentially we try to address these problems like timeliness, performance and safety, and in terms of target areas are these ones that you can see. So real-time safety, advanced cloud services and infrastructures, and cybersecurity and trustworthy ICT. So just very briefly, last slide about presentation. We have had in the past 10 years more or less involved in many projects, European projects. They are listed here. So you can see the last one, and I will be talking about the work that we did in Carrion. And currently we are involved in projects that have more to do with security aspects in the cloud. So as I was telling, we split the time between myself and Professor Rufino. I will be talking about the work that we did in the Carrion project. So here, essentially, I'll try to pass the message and explain to you what is this architectural hybridization idea that has to do with really looking at the system and understanding that it can be modeled in different parts. And this is important, a very important thing, we believe, approach to achieve safe cooperative functions. And this was basically the objective of the project. So in the beginning, we wanted to address systems, cooperative systems, not necessarily just in the airplanes, but also in terrestrial vehicles, and predictable and safe coordination of these smart vehicles that are autonomous and that cooperate with each other in order to perform some different functions. Of course, one of the things that is hard, and you can immediately perceive this problem, is that when we want to coordinate autonomous vehicles, whatever these vehicles are, they need to communicate over some wireless infrastructure, and in that sense they are subject to the problems of communication in wireless medium, so there's some kind of uncertainty that makes it more difficult to really predict what is going to happen and to make sure that things will happen as we want in a safe way. So in terms of the project goals and the work that we did was focusing on the architecture. We need to deal with these problems from the start, and then look at other things, of course, in the end validate and assess some of the results with prototype demonstrators. The partners involved, this was the quite small consortium with just 7 partners. I guess this Ashley project is really much bigger. So with the 7 partners, there was Embraer and GMV involved, so I think they are present here. And of course, in terms of use cases, we're focusing both on the air, avionics, UAS aircraft, and automotive domain. So some of the partners are more connected to the automotive domain. We had an advisory board that had Airbus, one person from Airbus in the advisory board, and also some people from VW and Volvo involved in the advisory board. If you want to see really some more results, there's a website of the project and some videos that we prepared in the end. Probably you will have copies of this presentation, and then you can follow the links to see the videos if you are interested. Okay. So the big challenge, and I would pose this challenge in this way, is that when we try to build these cooperative systems, it's important to always remember that they are cooperative, is to mix and to handle three important requirements at the same time. One of the requirements that we want the systems to be low cost, of course. That's always something that the industry is worried with. It's really reducing the costs of building these systems. And for that, of course, one of approaches is to try to use components that are not so expensive, that are, let's say, could be even off the shelf. And that immediately we perceive that there are some problems, because these components are not so robust and they can suffer from some failures. So this increases a little bit more the uncertainty. The other thing is that we want to develop systems that work very well, that achieve very high performance. And performance, you can some people, what do you mean by performance? If you think about, for instance, autonomous cooperative cars, and you think about the Google car that is around, so you can measure the performance by the speed that the car is driving all the time. And currently, they achieve to have these cars going in the roads, but at speeds that are really moderate, about 40 kilometers per hour. So for some people, this is really boring going around. So they don't crash that much, but they are really slow. And so this is not really just the performance that we are used to when driving a car. We would like to have better. So in order to keep the same levels of performance that we want with low-cost systems, then we have some risks. We incur in some safety risks. So to have these two bullets here, we have some risks. So the problem that we really try to solve is how can we build systems that, in one hand, can be built with not so that are low cost, have high performance, and at the same time are safe. So mixing all the three things is really a grand challenge. And for that, we started by defining, okay, so architecturally, we need to think about these systems in a different way. What can we do? So we know how a safe system is designed. That's pretty clear for all of us. So it's a system that you know everything about it. You know all the assumptions, you define them very clearly, and then you prove that given these assumptions hold, then everything will go as you want. So this is the typical control system, basic one. Everything is predicted in the beginning. You can do safety analysis, and then you prove that things will be safe. What we are doing here is we are, let's say, adding some more components. The other components are basically other cars that cooperate and then can provide more information. So we have increased information that comes from other cars, and we also probably even some components that we introduce in the car that are not so good and more complex for performing more computations. So we are including more components in the vehicle that introduce some uncertainty in the hope that we can, let's say, improve the overall performance of these autonomous vehicles, whatever they are, cars, airplanes, whatever. And when doing this, we are introducing some uncertainties and possibly some problems in terms of the safety analysis, because we cannot bound what is going to happen. We cannot ensure with enough certainty that communication will always be possible between the vehicles or between two airplanes that are in the air. Sometimes there will be problems of communication. So we cannot prove a priori that this improved operational mode with these additional components will really work as we want. So what can we do about it? What we did was to define, say that, okay, systems will be able to perform with different levels of service. A level of service is basically how you, let's say, what you expect to achieve with the function performed in a certain way. So let's say a level of performance in a car is when it can go up to 40 kilometers per hour. An higher level of performance is when it can go drive up to 100 kilometers per hour. So these are two different levels of performance of a certain function, for instance, let's say in a platoon. So what we can do is then we know what is the level 0. The level 0 is the departure one where everything is exactly as we had before, completely predictable in the beginning, and this is the basic level of service that is proved to work perfectly under all circumstances, relevant ones. And then we have another level of service that is better, a better one, okay, with the additional components, and then what we need to define is some safety rules. So, provided that some safety, some rules, some requirements hold during the execution, then we can know that these components are performing well. So, for instance, if we are able to know that we are being able to communicate with a certain timeliness, this means that everything is perfect with the communication. It's probably an assumption that we stated to be able to perform in this level, and it holds. Perfect. Then we can operate under this level of service. And finally, we can add more levels of service with more components, and we can do, let's say, it's just like creating different systems, different control systems, and then what we need to do is to prove that each of these operation modes provides the needed safety, provided that the requirements, the safety rules are met. So we need to know safety rules. If the safety rules are met, then the system is perfect. There's just one other thing, which is changing and switching from one level to the other, which also needs to be proven that it does not put in risk the system. And so this is the underlying idea. And of course, as I was saying, we need to prove for each of those configurations or levels of service that it is safe. And this is the only thing we do in design time for each of these levels of service. For that to work, of course, then we need something else. We need a part of the system that is able to know which level of service is the appropriate one in each moment. So if something goes wrong, if some component is not performing well, then it's necessary that we switch to another level of service in which this component we get rid of it. So it is not used anymore in that configuration. And then we go to a level that is correct. This part of the system, we call it safety kernel. And one very important thing that we need to know is that this safety kernel must, in design time, a priori, must be proven to always work as we want. So all the properties must be satisfied in design time, because it is, let's say, a crucial component of the system that deals with the performance of all the system and the changes of the level of service. So we need to rely on it in order to be able to rely that the entire system with this adaptation will be able to perform well in runtime. This safety kernel, the main function, we can explain it in a simple way, like saying it's a component that is able to collect information in runtime from all the components in the system, and based on the safety rules that have been comparing with the safety rules that have been defined in design time, verify if they are being met and what is the highest level of service that can be, let's say, in which the system can execute. So the architectural pattern that we defined was this one, where basically this part on top is it's the normal vehicle with the several components and so on, and this part below here is the safety kernel, the special component that is controlling the behavior and the different configurations of the normal system. This can look at it as if this was an aircraft or a vehicle. Then there's the part that I would like to come to, which is the hybridization line. What is this? It's, let's say, we know that some of these components are probably not, let's say, as good as we would like. They can fail in runtime. For instance, the communication with the other vehicles can fail in runtime. So we put them above the hybridization line, which means we cannot set bounds for these components in design time. We cannot prove that these bounds will hold. So they are above the hybridization line. Everything that is below is all the parts of the system that we are able to prove in design time that they will execute exactly as we want and satisfy all requirements. any normal real-time embedded safety-critical system. Okay, and these are the normal. This part. We always need a system, a car, an airplane, whatever, to have some components below this hybridization line, because this is how we can ensure that there is always at least one operation mode that is safe, that is proven, that it will always provide the needed safety. If everything fails on top, we can switch to a level of service that only uses these components. And that's it. And then there's the control loop to control the behavior, where we collect, extract information. We did some, of course, the project was not only this. I'm just talking about what we in our group mostly did, defining this and then implementing. But of course, it's important to, let's say, we did more things, and one of the things was to, let's say, define how we can know if the components are performing well. And what we did was to define a concept which it's basically abstracting the different failure modes of the components. And we say that we extract a validity information, that's what we say, and we are able to characterize data and the operation of components against a certain, and say there's a certain validity. And this is abstract for all components, and then there are methods for doing that. And based on this validity information and the component health, like timeliness, we are able to compare with the mentioned safety rules that were defined in a priori design time. And then there's the level of service adjustment. We have to tell the system must be prepared for that to adjust the behavior in runtime. Of course, this loop must be bounded in time. We cannot simply expect that the system will adapt when it wants. And so it's necessary that this will adapt. And this is not a problem, because part of the system is real time. So we know that things will perform timely as we want. So even if some of these parts does not respond, we are able to switch level of service until we reach the lowest one. Anyway, the time that this loop takes is very small, typically compared to maneuvers, both in the ground and in the air. And so even if this takes some time, it's always much shorter than the time a real maneuver takes. And so typically this is really not a problem. So some specific components, taking a closer look at the safety kernel. This is actually the entire system, an entire system with some abstract components of the system, and this is the safety kernel, and some of the parts that are inside the rules database with the safety rules. And then what we do is we have here this data validity from all the components to be able to test if they are performing well. Some timing failure detection data. Basically, these are heartbeats to test if the components are performing correctly on time. There's a module, because we are talking about cooperative systems. So when we say that there's a level of service, an operation mode, this operation mode should be agreed by all the vehicles that are cooperating. And this means that we need some kind of agreement, and this is done here. It's not inside of the safety kernel, because we cannot absolutely predict that this will work always correctly. In an extreme perspective, if this does not work correctly, we are not able to reach agreement between these vehicles, then we need to switch to a mode that is autonomous, completely autonomous. We tested this in real settings with some vehicles, small cars, but actually these were built by the University of Chalmers in Sweden, and for purposes of demonstrating, we just considered two operation modes, one which is autonomous, completely autonomous, and another one that is cooperative. It's hard to read this, but basically there's a cooperative module here, cooperative driving, and an autonomous driving below. This is the safety kernel, and this is what the system is doing. So the same things that I was showing before, but doing on a real system, software system that is running in these vehicles. Our part in the faculty, we developed this safety kernel module, and we had this board. It's basically an FPGA development board. So we developed the software, we put it running there on a soft processor, Leon 3 soft processor, which basically it's according to some, it's used in several domains. And then the operating system, our teams running on top to provide some of the needed real-time guarantees. And this was a mock-up, so the communication between the two parts was an Ethernet interface. We made it more robust to make sure that it would work and would not suffer failures and would be timely as much as possible. So with a lot of redundancy there to make sure that it would work correctly. And then, while Rufino is preparing to the second part of the talk, I would like to add a little more that we have done. I have not put here, but probably I can show you. We worked also with Embraer, and I know I'm talking about this because I know you probably are interested on that. We worked a little bit Embraer, but not on a real demonstration scenario because, of course, it would be hard to develop a real aircraft with these things. But what Embraer did was to create a simulation with an aircraft and some UAVs, and show and implement then some modules in the simulator that would, let's say, simulate this safety kernel and some real functionalities within the aircraft and the UAV. And then by injecting some faults on some of the components like the GPS and the communication module to the ground station, they would bring the system to a state where it would need to adapt between the different levels of service. And with the simulator, it was possible to see that the trajectories of the airplanes would change, of course, as expected, being less aggressive and more safe, giving more safety distance, because in the air, that's what we can do to be more safe, allow more safety distance, to increase the safety distance as soon as a failure was detected, and showing the principle that we wanted to demonstrate with this architecture. And so that was basically it. Of course, I will come back here after Rufino presents so that I can answer your questions if you have any. And thank you for my part.
I don't have at this time too many results. There are more research directions, research ideas than actual results. So the topic of this part of the talk is centered on the air architecture. It was a joint work with GMV. And the air implements a IMA-like architecture. I'm sure that you today here talk a lot about IMA. This is our IMA-like architecture. And we have implemented time and space partitioning, and also space partitioning. And we have two, let's say, adaptability mechanisms. One is directly inspired from the ARINC 653 specification, that is mode-based schedulers. That is the ability of the system to adapt to different modes or to different phases of the systems in terms of timeliness requirements. It also is designed to possible adapt to component failure. The other one is process deadline monitoring. Applications are designed around process by a group of processes, and for any reason, either because they fail or because some component fails, those processes may not meet the corresponding deadlines, the deadlines that are obliged to meet. And we have mechanisms to detect these violations of timelines, implemented in software. So both of these components are implemented, are software-based implementations. In a completely different line of work, we came up with the idea of non-intrusive monitoring. That is, try to assess the system in a completely non-intrusive way. And we came up with the idea of including in the system an observer that observes, for instance, the system bus, observes the communication between the CPU and the memory controllers, observes the communication between the CPU and the I/O interfaces. That's observing what is going on on the system. And we have implemented this in a non-intrusive way. The observer is non-intrusive with respect to the system. So we have a set of observation points that monitor a set of objects of interest, for instance, a variable on a program, for instance, a function call, for instance, an operating system call, and so on. Okay, so those are the objects of interest that we want to monitor. And we have a set of tools based on open tools, based on bin tools, to extract the information that we want to monitor. To extract, let's say, the observation points. Those observation points are basically memory addresses. Okay, so the observer observes the bus and has a set of observation points that we are interested to observe, and if those observation points are observed, the observer records an event. Okay? And of course, we can then observe those events externally to the architecture. So at this point, we came up with this idea. Can these non-monitoring functions be relevant for email-like architectures, to not only to assess email-like architectures, but to include it in the design of email-like architectures in order to improve their features, their characteristics. We know that nowadays systems are increasingly complex, that they are hard to verify at design time. So the question was, would this or those kind would this kind of system be relevant to improve email-like architectures? And we think that the answer is yes, of course. And it opens room, this non-intrusive real-time operation opens room to support runtime verification purpose. Okay. So the idea is to include an observer in the system that is specifically tailored to email-like architectures, in fact, to TSP systems, and use this in a dual way. Okay, so we may have hardware components. We have two parts of the system, let's say. One is the functional part, is the operating part. The other one is the runtime verification part. And we may have functional parts that are hardware-based, functional parts that are software-based, functional parts that are hardware-based are verified by minimum intrusiveness software components. Of course, here we cannot ensure that the system is not fully non-intrusive, but we have software. May have software-based functional system components that those are checked, are verified in runtime, or their operation is verified in runtime by hardware non-intrusive components. So for those two mechanisms, for mode-based schedules and for process deadline verification, we have analyzed them, and we see here that there is a gain in putting this operation or putting this verification in hardware. It's not a big gain, but these figures are only considering the time partitioning part of the system. Is not considering the spatial segregation part. We hope that with these new capabilities, we can improve, in fact, the behavior of the system. So I have a small video to show, and I think that I'm almost in time. So this is a prototype. This is a prototype of the air, and we have here one operating system, other operating system, a force operating system. So a system with 4 partitions that illustrate those architecture features that we did have in the previous slides. Okay. Thank you for your attention. I don't know if there are any questions.